Hello, my name is Michael and welcome to Dong, the first and only YouTube channel made by, of, and for teens who like cooking. Today, we're gonna be talking about babies. Babies are being born all the time. In some countries, they're born more often than others. This website, neil.fun/babymap, lights up each country on Earth at the same rate that babies are born in that country. So as you can see, India and China light up a lot. If you watch long enough, you'll get a little UK blip. That's a baby being born. I mean, not like, it's not an exact baby, but the countries light up at about the same rate as the country's birth rate. So you can really get a sense of where people are being born. You know, to be honest, humans are like one of my top 10 favorite animals. Let's keep talking about humans and how many of them there are with population bracketology. This website sets up a bracket of cities, and then it's your job to figure out who would win in a battle of who's got the largest population. I'm gonna change it from metro area to state population, make a new game. Some of these states have bye weeks, but let me see here. Between North Dakota and Illinois, Illinois clearly is gonna win. It's got big cities, it's got Chicago. You click Illinois, there you go. Now between Idaho and Vermont, Vermont is not very populated, but Idaho, I'm gonna go with Idaho. Phew, close one. All right, between New Mexico and Massachusetts, Massachusetts definitely has more people. And between Idaho and Massachusetts, obviously Massachusetts does. But between Illinois and Massachusetts, we've got Chicago versus Boston. And that Boston metro area is quite expansive, but I'm gonna go with Illinois. Boom! Chicago's like the #3 most populated city. I will keep playing this on my own time so I don't waste yours. We need to move on to outer space, specifically people who have been there. Travels in time and space allows you to look at astronauts from all over the world, from every country, even the commercial and tourist astronauts. Right now, I have my axes built so that I've got the length of trip on the vertical axis. The further down we go, the longer the person was in space. And the horizontal axis is when their first launch occurred. So if we go to the very furthest dot and click on it, Yuri Gagarin, first human being in space. He only spent 0.08 days in space, so he's, well, didn't have a very long trip. If we go to more recent launches, you'll see that some of these dots have white circles around them. Those represent people who are currently in space. Astronaut Scott Tingle, what's up? You, obviously, you little astronaut. Okay, astronauts don't just travel through space, they also travel through time, like we just did. My beard's longer, my shirt's different. Continuity isn't really a priority here at Vsauce headquarters, but what is a priority is learning. Let's take a look at this graph and change the horizontal axis to represent time dilation. There is clearly some function that defines how you move through time when you are moving through space and where you're moving through space. Check this out. The world record for longest time in orbit is held by cosmonaut Padalka, who spent 878.48 days flying very quickly around the Earth. And because of that, Padalka is about, well, more than 25 milliseconds younger than he would have been if he'd stayed here on Earth. That's because of time dilation. Now, when you're in orbit, time moves for you at a different rate because of two different effects, special relativity and general relativity. If you want to learn more about these, I highly recommend these books. First of all, Martin Gardner's Relativity Simply Explained, fantastic. But my favorite book that I read in all of 2017 was Lewis Carroll Epstein's Relativity Visualized. Just phenomenal. But if you want to get even deeper, you can go a lot less wrong than getting the Taylor Wheeler Space-Time Physics book. Just unbelievable explanations. We've also got videos linked down below where you can learn more, but the gist of it is this. When you are orbiting around the Earth, you are moving faster than people who are just still down on Earth at rest relative to you. And that means that time moves more slowly for you. A person at rest down on Earth, if they could take a telescope and look at your watch, would literally see your watch moving more slowly. You would be aging more slowly. You would be reaching your date of death slower. But also, the higher up you go, the weaker the gravitational field around you will be, and that will cause time to go faster for you. These two effects combine into this blue line that we see here. This red line represents time dilation due to orbital speed. And as you can see, the larger your orbital altitude is, the less quickly you have to move to not crash into Earth, and so the smaller the effect is. Now this green line represents the general relativity effects, the gravity well getting weaker, and as it does, you move through time faster and faster and faster. Their combined effect is this blue line labeled net orbital time gain. Now, astronauts in the International Space Station are at about, this altitude, a few hundred kilometers, and that puts them on the blue line down here, meaning they experience less time than us down on Earth. That's why Podolka is about maybe 30 milliseconds younger than he would have been had he not gone into orbit. If you'd like to see how you have been moving through time, Time Warper will help a lot. The University of Surrey created this app, and it takes information about your altitude and motion to compare how you have moved through time since installing the app compared to someone who has spent that entire time motionless at sea level. Fun fact, about 3,200 kilometers above Earth's surface, a little shy of 10,000 kilometers away from Earth's center, both effects exactly cancel out, and no time dilation is experienced relative to someone at rest down on Earth. Anywho, I'm sure you have a lot of questions. For instance, Michael, that's cool, but what I don't understand is how long can a zucchini grow? I'm glad you asked, because the world record for longest zucchini was set by Giovanni Battista Scozzafava of Niagara Falls. He grew a zucchini 2.52 meters in length. It's just phenomenal, but it's actually not that weird. Zucchinis like to grow big, they just don't taste great when they're large. Ideally, zucchinis are picked when they're young, no more than 12 inches long. So, if you're taking notes, don't forget that one. Now let's go back to light speed. When you're traveling really quickly, all kinds of weird relativistic effects occur, okay? Time dilation happens, obviously, but also measured widths change. Here's a relativistic car. Now I can use this slider here to make the car's velocity slower or faster. I can speed it up, and notice that as I speed it up, the car appears to contract and become thinner and thinner and thinner until at the speed of light, boom, it doesn't have any measurable dimension in its direction of travel. Now we've heard this before, and I've talked about it before in episodes about whether the Earth is flat or not. To a particle traveling near the speed of light, the Earth would be measurably flat like a disk, but would it appear to be a flat disk? No, because of an optical illusion known as a Terrell rotation. Here's an example from Wikipedia of what that looks like. I think this animation is brilliant. So on the right, we have the actual visual appearance of a cube flying by at some proportion of the speed of light. And on the left, we have the contraction, the actual width of it that we would measure. But notice that at 99% the speed of light, it almost is completely rotated so that we see the other side of it. Here's a way to visualize what a Terrell rotation is and why it happens. Here's a cube. Now let's imagine that this cube is just moving right past you. At some point, it's going to be right in front of you, and then it's going to move away. Now, normally, it would look like this. It's not moving very near light speed. You can't see the back of the cube. I mean, you can because this one doesn't have any opaque sides. But the point is that material over here isn't reflecting light to your eyeballs. We can imagine that this green stick is a ray of light. Any light coming from this back edge right towards you, it's getting blocked by the fact that the cube or the shape, whatever shape it is, might be opaque. But if this stick represents how far light travels in a second, and it's got to travel like this to get to your eye, if the object is moving near the speed of light, it might be able to move out of the way of that beam of light and not block it, so it will reach you. You'll see the back of the object as if it is actually rotated. So an object traveling near the speed of light will appear to rotate like that. That's only its appearance. It won't actually be rotated, and if you tried to measure it, you would find that its length had contracted. Let's watch a video of this effect. Spacetimetravel.org has a great one, and what you're gonna see is a bunch of dice, and they're all in a row. But then above them, a die is gonna fly by. I think actually a few die, known as dice, will fly by in the same orientation, but they won't appear to be in the same orientation. Here they come, all right? Not looking too weird yet, but as you'll see, the closer they get to us, the more rotated they are until boom, right there, we can actually see the back of the cube, even though the back is not facing towards us. This relativistic effect is called a Terrell rotation. and I love it. When it comes to relativistic effects, who can forget red shifting and blue shifting of electromagnetic radiation? Not us, right? And also not Velociraptor. In this game, the speed of light is much, much, much slower. So the normal speed a Velociraptor can move at is quite close to it, so relativistic effects occur. Now here's the level, and what I need to do is get to this yellow exit door. But wait, these bullets are kind of close together. I should probably be able to fit through them. Let me start moving. My velocity will change. Oh, and look, the entire game level warps according to how length changes, which means if I go up, the bullets get closer together. I can spread them out by moving down. Now I've got room, great. Whoa, 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 whoa. Okay, you don't want to fall in the water. If you ever want to center yourself on your character, I think you press C. Yeah, okay, there you go. I find this interesting, but not nearly as helpful. Press C again to go back. Also, notice that my velocity, it's like I'm playing asteroids. If I stop pushing the key, I keep moving at the same velocity, but spacebar will freeze yourself. I'll save your life many times. Now let's look at these keys. In order for me to open up this lock, I need all of the keys to have the same color, which means I need to find the velocity that red shifts and blue shifts them so that they match. Now, remember, velocity is a vector, so there's also a direction to it. So I don't just need to have the right speed, I need to be moving at the right speed in the right direction. All right, I'm able to get these two near in color, but how do I, okay, for that one I have to move left and right, I think. Now I'm getting it really too purple. Oh wait, that looked, but I don't want to move towards the bullets. All right, so moving to the right is the opposite of what I want to do. Let's see what I can, come on, change color. Yes, nice. And that's how you do it when you are an expert at the ways of the universe. I'm gonna leave you with, well, honestly, a bit of motivation. We've all heard of the company Arm & Hammer, right? They were founded 151 years ago. The brand was in use about 31 years before the birth of a man named Armand Hammer. Yeah, no relation. He had nothing to do with founding the company. It wasn't named after him. But as you can imagine, good old Mr. Hammer, Armand, to those who were familiar with him, got constantly teased for having a name that sounded like the brand, Arm & Hammer. So what did he do? Well, when he got older, got enough money together to buy enough stock in the parent company of Arm & Hammer to become a part owner. That's right, so Arm & Hammer became a board member of Arm & Hammer. So, my question for you is this: what are you doing today that will be strange enough that one day it might be discussed on Dong? Stay curious, stay hungry, be sure to preheat your ovens, and as always, thanks for cooking. Bon appetit.